Okay, today we're going to talk about how to algebraically solve now for discontinuities and asymptotes. So it was pretty easy to see from a graph just based off of whether you had a hole, a removable, or which is a removable discontinuity, a jump, or a vertical asymptote, which was an infinite discontinuity. So now we're going to talk about how to do it just from actual equations. So first and foremost, the first thing you want to check for are removable discontinuities. And how we do this is we first factor the numerator and denominator, excuse me, if possible. Okay. And then if there are factors that cancel, set those equal to 0 and solve, because then those factors would result in a removable discontinuity. All right, next we're going to check functions for infinite discontinuities. Okay, and you have the same first step, so factor the numerator and denominator if possible. Then if there are factors in the denominator that don't cancel, set those equal to 0 and solve. And then those would be vertical asymptotes, or where you would have an infinite discontinuity. All right, last step. Finally, we have to be able to check our functions for horizontal asymptotes. Okay, if your leading degree of your numerator is greater than the leading degree of the denominator, so like in example 7, that would be true, there is no horizontal asymptote. Whoa, not horizontal, horizontal asymptote. Okay. If the leading degree of the numerator equals the leading degree of the denominator, there is a horizontal asymptote at y equals their coefficients. So coefficient of the top over the coefficient of the bottom. Lastly, if your leading degree of the numerator is less than the leading degree of the denominator, there is a horizontal asymptote at y equals 0. All right, now with all that information, we're going to try some examples. So for these 4 following examples, we're going to determine whether the following functions are discontinuous, or excuse me, where they are discontinuous, what type of discontinuity occurs there, and then find any horizontal and vertical asymptotes. So the first step in finding any of this is to factor if possible. So if I factor this, I get x minus 5, x plus 1 on top. And then I get, I still have my x plus 1 on the bottom. So I have a set of factors that cancels. So that is a removable discontinuity. So very removable. And then to figure out where that happens at, you just set the factor equal to 0 and solve. So I have a removable discontinuity at x equals -1. All right, there are no more factors left in the denominator, so I won't have any vertical asymptotes or infinite discontinuities because I have nothing left in the denominator that cancels. And then the last thing we have to check for, is for horizontal asymptotes. So in this one, my leading degree of my numerator is greater than my leading degree of my denominator, so I have no, vertical asymptotes, and I have no horizontal asymptotes. Okay. All right, let's do the same thing down here for this next one. So again, you're going to factor if possible. So on the top, I have an x minus 2 and an x plus 1. And then on the bottom, I have a 1 minus x. Okay, so I don't have any factors that cancel. So I have automatically no removable discontinuities. I do have one factor in my denominator that doesn't cancel, so I'm actually going to have a vertical asymptote. And to figure out where that happens at, I set that equal to 0. So at x equals 1, I have a vertical asymptote. And then again, we have to compare the degrees, the leading degrees. So I have my biggest degree is in the top, so my leading degree of the numerator is greater than my leading degree of the denominator, so I have no horizontal asymptotes, again, in this one. All right, let's look at example 9 and example 10. So in example 9, let's see. I don't think there's anything we can do. Nope, no factoring can be involved, so automatically I'm going to have no removable. All right, now let's check for, let's see. I have a factor in the bottom that we'll see if I'll have a vertical asymptote there. But the only thing I notice about my factor in the bottom, and you'll see this in a second, is if I try to solve for where that vertical asymptote is, I'll get x squared equal to -7, and you can't take the square root of a negative number. So I actually have no vertical asymptote either, no real one. I have an imaginary one, but no real one. All right, and then last but not least, to check for horizontal asymptotes. And so let's see, I have my leading degree is now in the denominator, so automatically if my leading degree is in the denominator, that means I have a horizontal asymptote at y equals 0. All right. Okay, last example. Looks like I got quite a few things to factor. So up top, I got x. Let's see. What multiplies 12? 3 and 4? Perfect. X plus 3, x plus 4 gives me 7 when I add them together. In the denominator, I'll have what multiplies to -20 adds -1. So x minus 5, x plus 4. All right, automatically I have a removable because I have factors that cancel. So I have a removable at, it looks like x equals -4. And then I also have a factor in my denominator that doesn't cancel, so I actually am going to have another vertical asymptote as well. X minus 5 equals 0. So I have a vertical asymptote at 5. I have a removable discontinuity at x equals -4. And then to compare my horizontal asymptotes, I look at my degrees. My leading degrees actually match here, so I'm going to have a horizontal asymptote at their coefficients. So y equals 1 over 1, which is just 1. Lovely. All right, let's look at some more piecewise functions just to make sure that we're good with checking if they're discontinuous or continuous. And so we're going to go through the same kind of 3 steps that we did previously. So for piecewise functions, the first thing you have to check is f of 3 defined. So if I actually plug in 3, I would plug it into the numerator, and I would the square root of 3 plus 1, square root of 4, 2. All right, check, we're defined. Then I'm going to check to see if my limit exists, and I'll have to check my left and my right hand limits, because it's a piecewise function. My left hand limit would use the top equation again, because that's for values less than 3, so slightly less than 3. So my left hand limit would be 2, and then my right hand limit would be, if I plug it into the second piece of my piecewise function, for values slightly greater than 3, I would get 5 minus 3, which is 2 again. All right, so my left-hand limit equals my right-hand limit, so check my general limit exists, and then my general limit does in fact equal my function. So it passes that third step. X approaching 3, my general limit equals f of 3. So check, we would say that the function is continuous at 3. All right, do the same thing for the next one. F of 1 means I actually plug in 1, so I look at where it's equal to 1, so I get 1. Let's see, my left-hand limit would be the top piece, because that's for values less than 1. So x approaching 1 from the left-hand side would be, if I plug in 1 there, I get negative 2 times 1 is negative 2 plus 3, which is 1. And then if I plug it into my right hand, I also get 1 because that's be plugging it into the second piece right here. So down here, 1 squared is 1. And then last but not least, my limit, general limit, because my left and right hands match, my general limit would actually equal what my function is when I plug it in. So this is continuous as well. All right, last little piece down here, example 13. If I find f of 2, means I'd actually plug it in where it can equal 2, so I'd get negative 4. Check, defined. My left-hand limit would be also in the top piece, so I'd get negative 4. My right-hand limit would be in the bottom piece this time because that's for values greater than 2. So if I would plug 2 in there, 2 times 2 is 4 minus 8, so that's negative 4 plus 1, right? 4 minus 8 is negative 4 plus 1 is negative 3. Oh no, my general limit doesn't exist, so this is actually discontinuous. And then we stop there.